Hello everyone, today I'm going to show you my first provisorical version of the Cavendish experiment. Now the Cavendish experiment is an experiment that allows you to measure the gravitational pull between two rather everyday life-sized objects like few pound objects that you can actually have and move around and put on a weighing machine, and it allows you to measure the gravitational pull between such small objects under rather normal conditions without any high-tech equipment, which I always found quite fascinating. Now, when the Cavendish experiment was first performed in the late 18th century, that was quite a breakthrough. Now, I'm not really going to go into the history, but at the time, gravity was not really as well researched as today, and especially even though you had an idea that apparently the Earth had mass and attracted objects, and thus through gravitational pull things would fall down, you could measure quite well how quickly things fall down, the gravitational acceleration of the Earth's gravity at surface level, but you couldn't really measure the Earth's mass or the gravitational constant for that matter. You could measure the relation between those two because you knew roughly how big the Earth was, so you knew your distance to the center of the Earth. So if you knew the Earth's mass, you could calculate the gravitational constant and vice versa. And the Cavendish experiment actually was basically the first way to determine the gravitational constant, which then also meant that you could determine the Earth's mass and thus, given the Earth's size, also the Earth's density, which was quite a breakthrough. And of course nowadays we have better ways to measure such things, but and the gravitational constant, even though it is actually the least precisely known universal constant there is. So we've measured all the universal constants we know, and with modern lab equipment we can measure most of these to incredible precision, but we can only actually measure the gravitational constant to an accuracy of about 1/20,000th, which is still really precise, but for today's scientific standard it's relatively inaccurate to compared to how precisely we can measure other things, which is of course because gravity is a relatively weak force, at least compared to the amount of mass you need to actually create that gravity. Now, there are several versions of the Cavendish experiment, and they vary in accuracy, and of course, since it requires a very precise measurement, there are always slight disturbances through wind or vibration. But you can actually roughly estimate how well you could measure the gravitational pull between objects even without knowing the actual gravitational constant. Uh, we know that gravitational pull is proportional to mass, and that at a similar density mass is proportional to volume, and a remotely similar shape that can be approximated as a size to the power of 3, and we know that gravity is proportional to the invert of distance cubed, and we are quite away from the center actually. So in fact a smaller object of a similar density, assuming the same shape, actually has a surface gravity that is proportional to the radius of the object, and that's actually not that extreme. That means that really small objects still have a surface gravity of a fraction of a millionth of the Earth's gravity, but that's actually still a lot if you then put in acceleration, and of course the way an object travels under constant acceleration is also proportional to the time squared, so you can kind of take the root of the distance you want to travel divided by acceleration, and in a few hundred seconds you can actually make a few millimeters, even with a gravitational pull of just small everyday objects. Now, the way the Cavendish experiment actually measures the force of the gravitational pull is through a torsion wire or something similar. So you have some kind of wire or string that can be twisted, but only with some torque. But it only takes very little torque to twist it a tiny little bit, because it's a very thin wire, and you suspend a long lever from these thin wires, and then you can kind of balance that long lever. It doesn't have to be perfectly balanced, but it has to hang from this wire, and it has to be relatively long, so it should be sort of balanced. You put two smaller weights at the end of these. Doesn't really matter how big exactly those are, they just shouldn't be carried away by the tiniest bit of wind. And then you can add big weights that you know how heavy they are, and you can then calculate how strong the gravitational pull of those weights on the smaller weights is by measuring how much the wire actually twists. And of course it's very difficult to actually put the lever into perfect stillness, so it will swing back and forth a little bit in the beginning, but even with that you can still get a good idea of how strong the gravitational pull is if you make several measurements and take averages, or if you actually analyze how it moves, and you can measure how far it swings and where the maximum and minimum, or the two maximum deflections of this swing are, and you can then put in the gravitational weights, and after it gets pulled towards them, after it has kind of dampened out a bit, you can then measure where the two maximum deflections of the swinging are now, and where the center of that swing are now, and you'll see that it will have moved according to, again, the torsion and the amount of torque applied by the gravitational weights and their position towards the weights at the ends of the lever. Now, for the first try, I rather provisorically used some lead solder as a torsion wire, and a combination of heavy stone plates and a bucket full of water, and these metal weights as gravitational weights. And even though that's not perfectly accurate yet, and the lever still swings around a bit, you can already see the gravitational pull if you look at the time lapse and you look at where the swinging stops, or where the maximum deflection of these swings are. You can see that usually after the gravitational weights have been in place for a while, the center of these swings is about 1 or 2 centimeters further to the right, or closer to these weights, than after the gravitational weights have been removed for a while. Now, of course, when you first put them in place or remove them, it's going to move rather wildly, because it's just being deflected further by removing or adding a force, and thus shifting the center of what is essentially a pendulum with an additional force on it. Now, I'm still going to put some further analysis over this footage, and also try to improve the setup itself. But for now, I think this is actually quite fascinating, because you usually hear of gravity as this really weak force that you can feel the gravity of celestial bodies like the Earth, or other celestial bodies, because they're very, very big, but we usually think of the gravitational pull of everyday objects or other smaller objects as pretty much negligible or insignificant, but here you can see that you can actually see the gravitational pull of an object that you could actually carry with your hands. Now, I might still do a few more experiments with this kind of rig, and of course I'm always open for any questions or suggestions, and as always, thanks for watching.